You selected answer C, which is the correct answer, that we're going to expect an increase in conversion and that it could actually be above 40%. So to see why, it's actually easiest to analyze this problem graphically. And what we're going to plot is on the y-axis the conversion in the reaction, and on the x-axis the temperature inside the reactor. And we know that for an exothermic reaction system, that the relationship between conversion and temperature should be that equilibrium conversion will decrease as the temperature increases. And so qualitatively we can sketch the plot like this, where the equilibrium conversion at low temperatures is high and the equilibrium conversion at high temperatures is low. Now our reactor is going to operate on the left-hand side of the equilibrium curve. We're going to start at 0% conversion in the reactor. And so at 400 Kelvin, we can see that what's happening is that we have the feed enter at 400 Kelvin. Because it's an exothermic reaction, both the temperature and the conversion increase as we go through the reaction until we reach an equilibrium point. And that equilibrium point, it turns out, is at 40% conversion. And we know this because when we decrease the flow rate by a factor of 2, and therefore increase the amount of time that the fluid spends in the reactor by a factor of 2, the conversion is 40% for both of those cases. So increasing the amount of time in the reactor is not improving the conversion, and so we've reached the equilibrium limit, and we're stuck at 40% conversion. Now, when our feed temperature is 350 Kelvin, we can start increasing the temperature, and the rate of reaction should initially be lower, because the Arrhenius dependence of the rate constant dictates that the rate constant will have a lower value at 350 than 400 Kelvin. And so in the initial condition, we know that we get a conversion of 35% when we have a flow rate of 1.5 liters per second for the feed. We don't get to as high a conversion because the reaction is slower at the lower temperatures at which we're operating the feed. However, now when we increase the amount of time that the fluid spends in the reactor, we are no longer limited to the same extent by equilibrium. So we can potentially approach a higher equilibrium conversion, right? But we can potentially get up to an equilibrium conversion of greater than 40% because we're starting at a lower adiabatic temperature. So for this reason, we expect that lowering the flow rate and therefore increasing the amount of residence time of the fluid in the reactor can get us to conversions greater than 40% for this reactor.